now that we have relationships between rectangular and spherical coordinates, and also cylindrical, but I want to focus on rectangular and spherical right now, I'd like to describe a region in space using spherical coordinates. So I'm asked to describe the snow cone in space bounded above by the sphere x squared plus z squared equals 4, and on the sides by the cone z equals the square root of x squared plus y squared. Let's see if we can picture the region first, and I'm going to imagine a sphere first. And so there's my sphere of radius 2 centered at the origin. So apparently the snow cone I'm talking about is bounded above by this sphere. So I'm introducing my x, y, and z axes now, and I know these points, these intercepts, are at 2 units out on their respective axes. I learned a long time ago it's easier to draw a sphere first and the axes second, so it allows me to get a moderately good sketch. All right, now I need to think about the cone. Well, this cone, z equals the square root of x squared plus y squared, is just the cone starting at the origin, coming out at a 45-degree angle in all the coordinate planes. If I think about y being 0, I would get z equals the absolute value of x. And the same thing if I let x be 0. So I just get a cone that would look like this. Right, so I spin that around, and so I see the top of the snow cone in blue and then the cone part in red. And so all together I could imagine there's my cone, and then just the top lens of the sphere above where they intersect. I haven't done a great job of drawing this, but I think it works fairly well. So there is the snow cone region I'm talking about, and now I'm supposed to describe it using spherical coordinates. Well, this is pretty nice. Z is equal to r. Well, that's not spherical, that is cylindrical coordinates. But then I had one more relationship, and this would tell me that z is equal to rho sine phi. All right, so that's a nice relationship, and I'm thinking about the cone part. Well, I want rho's, phis, and thetas, and I still have a z in there. Well, I know that z is equal to rho cosine of phi, giving me this equation. I could divide both sides by rho, and I could then write this as 1 equals tangent of phi. Well, if phi has to be between 0 and pi, then my only option is at pi fourths. The cone is literally the spherical equation pi fourths. If I rotate down from the z-axis to an angle of pi fourths, and I'm allowed to rotate any angle any angle theta, I literally trace out that whole cone. And so that lets me know that in spherical coordinates, cones that look like this one, right, with their vertex there at the origin, would just be uniquely determined by saying an angle of rotation down from the z-axis. So if phi is equal to pi fourths, I could imagine rotating down. A rho would tell me how far to go out, and then spinning that around for any angle theta between 0 and 2 pi would trace out that whole cone. Well, now all I have to do is describe the top. Well, that's pretty easy. That's rho is equal to 2. So I'm bounded above by rho equals 2. And on the sides by the cone, phi is equal to pi fourths. And we've gone from a rectangular description to a spherical description. We're bounded above by the sphere, rho equals 2, and on the sides by the cone, phi equals pi fourths. And I think we can see some convenience in thinking this way. These two equations are simpler than the two rectangular equations.